We tend to think of the ground beneath our feet as, well, solid, a reliable barrier. But what really happens when something spills on the surface? It's not like it just vanishes. It actually begins this hidden journey, a super complex migration deep into the earth. And that journey has some pretty profound consequences for the very water we drink.
So that brings us to the big question we're tackling today. How does a contaminant, whether it's fertilizer from a farm or a tiny leak from a gas station, travel from the surface all the way down into our groundwater? Well, the answer is way more complex and honestly, way more fascinating than you might think.
And just to see why this really matters, take a look at this map. This is not some abstract theoretical problem. This shows nitrate contamination all across the United States. And those red zones, that's where groundwater has more nitrates than is considered safe for drinking water. So this hidden journey is already having a huge impact on communities nationwide. So let's figure out how it happens. Okay, to understand this journey, we have to start with the two fundamental forces that move these dissolved substances, which scientists call solutes, through the soil. They're called advection and diffusion. Advection is pretty easy to wrap your head around. The pollutant is simply carried along by the flow of water, kind of like a leaf being carried down a river. Diffusion, on the other hand, is that natural tendency for molecules to just spread out. They move from an area of high concentration to low concentration. Think of a single drop of food coloring slowly expanding in a glass of still water. So to put it simply, advection is the highway, and diffusion is the slow bleed into all the side streets. But what's really wild here is that advection isn't some simple, uniform flow. What you're looking at is a simulation of water moving through the tiny little pores between soil particles. The bright colors, those are the high-velocity hotspots. The dark blue areas, water there is practically standing still. So the ground isn't a simple pipe at all. It's this incredibly chaotic maze of superhighways and dead ends. But, of course, the journey gets even more complicated. It's not just about moving forward. Pollutants run into roadblocks, they get stuck, and they spread out in ways we have to try and account for. One of the biggest roadblocks is this process called sorption. It's where chemical and physical forces make pollutants literally stick to the soil particles. Certain pesticides, for instance, are really prone to this. Their journey is just constantly getting interrupted, snagged by the soil itself. And this slowing effect is so important that scientists even have a name for it. They call it retardation. So, while some pollutants are getting slowed down by sticking to things, the entire plume of contamination is also spreading out. This combined effect of being carried along and also diffusing outwards is called hydrodynamic dispersion. It basically means the contaminated zone doesn't just move forward, it also grows, becoming wider and more diluted as it travels. All right, now we get to what is honestly the biggest curveball in predicting where pollutants will go. The fact that soil is not uniform. Not at all. It's filled with secret shortcuts. And this whole phenomenon is called preferential flow. Preferential flow completely changes the game. It's when water finds these express lanes, completely bypassing the bulk of the soil and traveling deep underground way faster than our simple models would ever predict. Let's look at some incredible visual evidence of this in action. It's really something else. This is just a brilliant illustration. So scientists poured blue dye on this patch of ground in New York, and you can see it moved pretty evenly through the topsoil, but then, boom, it hit the subsoil and shot downwards through these really distinct channels. Those are macropores, old root channels and earthworm burrows that act like literal superhighways, funneling contaminants straight down. And here's another cause. This is a sandy soil that's become hydrophobic, which just means it repels water, probably because of some organic matter. So when it rains, the water can't just soak in everywhere. Instead, it finds these weak spots and just punches right through in these concentrated fingers, which you can see perfectly with the pink dye. This means any spill on the surface gets funneled and pushed right down these specific paths. And finally, the very structure of the soil itself can create these shortcuts. I mean, we expect water to go down, right? Gravity. But look at this. The blue-dyed water hits a sloping layer of coarse sand and is immediately funneled sideways. This completely changes the pollutant's trajectory, sending it in a direction you would never, ever predict without knowing about the hidden geology under the surface. So when you combine all of these complex forces, advection, diffusion, and especially these wild, unpredictable preferential flows, what do you get? You get the real-world result, our contaminated groundwater. Let's go back to that map from the beginning. Now it makes a whole lot more sense, doesn't it? Those red hotspots, like in the Great Plains or California's Central Valley,
are often in areas with really well-drained, sandy soils. In places like that, advection is super efficient, and preferential flow can zip contaminants like nitrates from fertilizer straight down to the water table with very little to slow them down. And of course, it is not just agriculture. The same principles apply to contaminants from a huge range of sources. We're talking about pollution from mining, industrial solvents, leaks from those underground tanks at gas stations, and even accidental spills of fluids used in oil and gas production. The list goes on. So let's bring this all together. After seeing these complex pathways and all these secret shortcuts, we really have to ask the most important question. Why does this hidden journey actually matter?
It matters because the big takeaway here is this. The ground beneath our feet is not the simple, reliable filter we often imagine it to be. It is a complex, unpredictable maze of fast lanes and roadblocks. Just assuming that a spill will be filtered out by the soil, well, that's a dangerously simple way of looking at it.
Which really leaves us with a final thought to chew on. Knowing just how intricate and unpredictable this journey is, how should that change our approach to protecting our groundwater? How do we manage what we do on the surface to safeguard a vital resource that's completely hidden from our view, following pathways we can barely even predict?